In the first video on partial differentiation, we saw that if we had some function z made up of two variables x and y, we could differentiate the function with respect to the first variable by keeping the second variable constant, or we could differentiate the function with respect to the second variable by keeping the first variable constant. Now, these two partial derivatives are themselves functions of x and y, so that means we could differentiate them a second time to give a second order partial derivative. So if we take the first partial derivative dz dx and differentiate this function with respect to x, keeping y constant, we get d2z dx squared. If we take this function and differentiate with respect to y, keeping x constant, we get d2z dy dx. Now similarly, if we take the second partial derivative dz dy and differentiate this with respect to x, keeping y constant, we get d2z dx dy. And if we differentiate it with respect to y, keeping x constant, we get d2z dy squared. So as you can see, there are four derivatives from a function containing two variables, as in this case, which are x and y. Now it can also be shown that the values of d2z dx dy are the same as the values of d2z dy dx for all functions which are continuous. So let's have a look at an example. Here we are given a function z which is made up of a product of two functions which have two variables x and y, and we're asked to find the second order partial derivative d2z dx squared, d2z dy squared, and also to find d2z dx dy. So to differentiate this function, we use the product rule and we let u equal to 3x squared minus y and v equal to 3x plus 5y cubed. So applying the product rule, dz dx becomes u, which is 3x squared minus y, times the derivative of v, which is 3x plus 5y cubed, plus v, 3x plus 5y cubed, times the derivative of u, which is 3x squared minus y. So differentiating 3x plus 5y cubed with respect to x and keeping y constant will give us 3. And if we differentiate 3x squared minus y with respect to x, keeping y constant, we get 2 times 3, which is 6 times x. So if we multiply this out, we get the following. And if we add 9x squared and 18x squared, we get 27x squared. So dz dx is 27x squared plus 30xy cubed minus 3y. Now, to get the second order partial derivative d2z dx squared, we differentiate this function again with respect to x, keeping y constant. So differentiate 27x squared, we get 2 times 27 times x to the power of 1, which is 54x, and differentiate 30xy cubed. Because y cubed is considered a constant, that's the same as differentiating 30y cubed times x, which is just 30y cubed. And when we differentiate minus 3y, which is a constant, we get 0. So the second order partial derivative d2z dx squared is 54 times x plus 30y cubed. In part 2, we need to calculate the second order partial derivative d2z dy squared. So once again, we use the product rule, again letting u equal to 3x squared minus y and v equal to 3x plus 5y cubed. Now this time, we differentiate v with respect to y. So differentiating 3x plus 5y cubed, keeping x constant, will give 3 times 5, 15 times y squared, and differentiate the u dy, keeping x constant, will give minus 1. So if we substitute these values, and if we expand, we get the following expression, and adding minus 15y cubed and minus 5y cubed gives the following expression. So the first order partial derivative dz dy is given as 45x squared y squared minus 20y cubed minus 3x. Finally, to get the second order partial derivative d2z dy squared, we differentiate this function with respect to y, keeping x constant. So differentiating 45x squared y squared will give 2 times 45x squared, which is 90x squared, and differentiate minus 20y cubed, we get 3 times minus 20, which is minus 60. Take 1 from the power, we get minus 60y squared, And if we differentiate 3x, we get 0 because this is considered a constant. So finally, the second order partial derivative d2z dy squared is given by 90x squared y minus 60y squared. Finally, in part 3, we're asked to calculate the second order partial derivative d2z dy dx. Now this is the same as writing the derivative of dz dx with respect to y. Now we already calculated the first order partial derivative dz dx in part 1, and this was given by this expression here. So we need to differentiate this expression with respect to y, keeping x constant. So differentiating 27x squared becomes 0. Differentiating 30xy cubed becomes 3 times 30, which is 90 times xy squared. And differentiate minus 3y, we get minus 3. So therefore, the second order partial derivative d2z dy dx is given as 90xy squared minus 3. So here's an exercise that you could try. Using the same function we had in the example, show that the second order derivative d2z dx dy is the same as the second order derivative d2z dy dx.